All right. So I'm assuming that all of you reviewed the material from last Thursday and now have a really good, thorough understanding of how instructions execute in the processor. That was I would call that a 40-60% joke. 40% joke and 60% more kind of serious. But really, I mean, that's kind of, that lecture, okay, is kind of showing you guys how to study kind of from this point on, okay? Because, I can write modules just like before, but the modules in text is going to be much more difficult to describe what is going on compared to, using the logic sim as a simulator. So that's kind of what is going on. So before I move on, just kind of for kakas, I want to see what you think of this thing over here. Okay. So just watch, you're going to, and okay. So wait, there's more. That's more. See, okay, he's doing a pretty good job, kind of showing people how that thing is supposed to be used. So I showed this to some people, and they basically, thought this is the most dorky thing ever, okay? Because it looks like a baby carrier, except you're not carrying a baby, you're carrying a laptop computer, so you can use it, while you're walking around. So you might think, who would want to do something like that? Who would want to buy something like that? Yours truly. Because when I go to the design hub, very often there's no space for me because the students are, rightfully using all the workstations. So what am I going to do? Because I need my computer, okay? Because I need to use a keyboard to kind of look for things on Google and whatnot. But I don't have a place to put my computer. Okay, I can put my computer, somewhere, but I would need it to look up stuff too when I walk up to try to answer a question at the design hub. So this is my ticket. I don't need my cell phone anymore. Oh, yep, that sort of works. Yeah, but this thing, it has a metallic, brace in the inside, so it's actually pretty solid in terms of construction. And it's designed for this purpose. I mean, that's what it's designed for. So I'm thinking, if it's not because that is expensive, I would have gotten one already. But it's a little bit on the expensive side, so I'm going like, maybe not. $200. Yeah. Yeah, if it's only like, $50 or $40, I might go for it. But since, okay, this is another tidbit, that you guys may not know, okay? In terms of all California community colleges, Los Rios is ranked second from the bottom in terms of faculty salary schedule. So there are 73 districts in the entire California, and we are ranked 72nd. Way to go! Only one more step to become the dead bottom. So we'll try our best to get there. So that's why the $200 thing may not be that affordable anymore. Okay. So as some of you may have heard, okay, from other professors, the district has also mentioned that we might, okay, depending on how things develop, we may have to close the campuses. But the district is currently thinking, let's move everything online because that's what the Europeans are doing. Okay? Seems to make sense, right? Except, no, with me, it's not that big of a deal. Okay? With me, you're moving this class entirely online simply means that I don't have to spend 15 minutes to drive here, park, and then walk all the way to the classroom. Okay? So that I can look at you guys while recording. Instead, I can be home in my PJ and record without having to drive somewhere first, right? And I don't have to shave every 3 or 4 days anymore. Like in 4 weeks, I don't have to shave at all. Okay? So I'm all set up because everything is on Canvas. Okay? I'm doing the streaming, and if we ever have to move online, I'll stream at exactly the same time slot, which means all of you should be able to listen to the live stream in real time, and I can look at the chat, on YouTube, or I can set up a Slack channel for this particular class, so I can be, eyeing on the, chat, and if anyone is asking a question in real time, I can address that in the video right away. So as far as this class is concerned, we might lose a little bit, in terms of interaction because I can't see you anymore. You have to type in order to ask me a question. But other than that, I think we're fine. Okay, we should be able to move online, and I think most of you at least have a computer that you can use to run Logisim, which is going to be the tool that we need, and it has to be internet connected because a lot of the tools that I have developed, they also require internet connection. But I think with this class we're okay. Okay. But what about the philosophy class where the professor is not even using Canvas? Everything is paper-based. What about that professor? How is that professor going to move everything online in a few days? What? Go ahead.
That sounds like that professor probably. He just mails it to you. He mails you the slides.
It's called class by correspondence. So everything is done by snail mail. Yep. Okay. So so the district has not quite decided what to do, whether to compensate professors who are moving face-to-face classes to online modality, and so there's a lot of uncertainty. Okay, so I'm not really sure what's going to happen, but if something is to happen, we are all set up. Okay, we're good to go. Okay, so what we'll do today is we are going to look at the processor again. So I'm changing the way I explain things this year a little bit. Before, in previous years, I used to explain each of these components individually in order to explain how the processor itself works. So this year, I'm going to do it a little bit differently. So this year, I'm going to use the simulator, run the processor, run actual instructions, and then in each step of running an instruction, I explain the components. So I'm doing it kind of in a reversed way. I apply first and then explain each component of how they work. So it's a little bit different from previous years. So let's go ahead and start with something that you might see tonight, depending on how much we can go over today. So let me go get Java started. Logisim. Nope. That's not the wrong one. That work. All right, so you get into Logisim first, and then you go to the processor file, which I'm sure most of you know how to do already because that's part of the lab from last Thursday, which is due this Thursday. Okay, so this is the processor. And we'll go ahead and take a look at RAM, and let me just kind of re-emphasize that RAM is where the instructions go. Oh, this reminds me one more thing. The context of this entire thing, okay? Because this kind of model where, we load the program into RAM, and then the program runs in RAM, to most of you, this is like, yeah, we get it already. We just don't know the exact mechanism, okay? But we kind of know that we need RAM in order to run programs. That concept turned out to be a novel concept at one point in time. Then you might ask, well, then what happened before? So before programs are loaded into RAM to execute, what you do to specify what a program would do is to open up the back of a computer and then change the wiring between the components of the computer. That is how you specify the operations in a computer, is by physically rewiring components. Yep?
Like an old-fashioned phone switchboard?
Yes, except you have a lot more connections. because you're basically rewiring components on the fly in order to change the behavior of the computer. Is that okay? So needless to say, okay, anytime you want to update a program is a major undertaking because just physically unwiring and then rewiring all those components is a lot of time. And if you get one wire wrong, it's not going to work. And there's no debugger to tell you, oh, it's this line here, the syntax is wrong. Nope, the thing is just not going to work. But which one of the 10,000, 20,000 wire is wired incorrectly? We don't know. Maybe it is wired correctly, except the terminal has oxidation and is not making good contact. That happens a lot too. Okay, so for those of you who have taken or who are taking ET or electronics technology classes and you have to do breadboard projects, oxidation is a constant battle. Okay, you just don't know whether the contact is good or not. All right. So who changed all of this? Okay, and that's why the passcode of the previous lab is called Johnny, because the person in question is John von Neumann. And I was corrected by a few people that it's not supposed to be pronounced von Neumann, it is von Neumann. So John von Neumann is the person who, this guy right here, is the person who first thought of, hey, instead of using memory to keep track of just the numbers that we're working with, why don't we also use memory to keep track of instructions that will tell the computer what it is supposed to do? Because that way you can change the behavior of the program just by changing the content of RAM or changing the content of memory, and you don't have to rewire things all day long. Is that okay? So that's why all computer, well, not all, but most computers today on your mobile, on your Fitbit or cell phone or your laptop computer or even mainframe computers, they're all using what we call the von Neumann architecture, which is basically saying we store the program, we load the program into RAM, and then the processor goes to RAM to figure out, hey, what am I supposed to do next? And then the content of RAM will then tell the processor and say, oh, you're supposed to add register A to register B, and then put the sum back into register A. Okay? So that has changed only because of John von Neumann. It probably has a history of his inventions. Okay, it has. I mean, this guy is super. Okay, even within geniuses or genii, he's different from all of the other ones. Because if you look into his contribution, it has set just within mathematics. It has all of these, and the nuclear weapons, computing, cognitive abilities. That's his capability, and he's also very different from what you would imagine as a genius, as a scientist. Okay, when people ask you, okay, what would be the iconic scientist? Okay, that most people know. Okay. There are a few. Most people would name Einstein, okay, or Bohr, okay, as one of the kind of iconic scientists, and they would not be wrong, okay. This guy cannot be any more different, because Einstein turned out to be at Princeton at the same time that this guy was also teaching at Princeton. They were in the same hallway. Einstein is an introvert, okay. When he works, he wants to be by himself and without distraction. This guy likes to listen to polka music when he works. So you can kind of imagine the not so friendly conversation between those two along the hallway. And it probably has nothing to do with quantum physics or relativity. It's like, your stupid music is too loud. I cannot even hear myself thinking. Yeah. I'm just guessing that's what happened. So anyway, so back to his contribution. The von Neumann architecture would not have been possible. In other words, forget about update or over-the-wire updates, which we all rely on today, right? I mean, how many times do you think your phone updates itself in terms of all the apps, the operating system itself, at least what, twice a week, daily maybe? Okay, so depending on the stability of the programs that you have installed, that would totally be not possible without his contribution. Because you're going to have to open up your cell phone, right? Put on your microscope, your gear, disconnect the components, reconnect all the components, and hope that it works. Sorry? Oh, we are not going to have surface mount anything, if that is the case, right? So that's just a little bit of background, that we are now kind of taking it for granted, okay, that, oh, we always run programs in RAM. What do you mean by we don't run programs in RAM? Well, there was a time that programs were not specified by content in RAM. Instead, they were specified by hardwired connections. So, yeah, there we go. All right, so in this case, we have a blank memory here. It is completely blank. It has nothing in it, okay? So what I want to do first is to show you the entire life cycle of how an opcode executes, okay? So you might want to pay attention, or you might want to kind of write down the time mark of today's lecture, because you might want to get back to this part from time to time, okay? So you look at this and go like, but there's no instruction to execute. Well, that is actually not correct. It is correct that I did not specify instructions to execute, right? But there's a difference between I did not specify any instruction to execute as opposed to there's no instruction to execute. Because RAM is reset to all zeros by itself, okay? If you do a control R, with the simulator, RAM is going to reset to all zeros, okay? That's just the quote unquote default reset state of RAM.
That means it doesn't have any stop commands.
Sorry?
It doesn't have one of those alt commands, which means it's just going to run whatever instructions
It will keep going. That is correct, okay? So we'll see that effect later on. But right now, we're going to say, but what program is this going to run? So if you look at the memory content and you want to reverse engineer and say, what are the opcodes, okay, what are the mnemonics corresponding to the opcode, this process is called disassembly, okay, which is the reverse of assembly. So disassembly is looking at the opcode, in this case in hexadecimal, but nonetheless it's really just one way to represent 8 bits in a much more concise way. So if you want to reverse and say, what does that say? Okay, if I execute the opcode of 00, what is it going to do? That's called disassembly, okay? So we can disassemble fairly easily, okay? We go to the opcodes table. And you have access to the opcodes table, and we talked about this last time already, but we'll go ahead and just go to that folder, which is already shared with you, all of you, inside processor. There we go. And we go to opcodes table. Okay. Opcodes. Oh, I just passed it. There we go. And the way you do this is you just look up and say, what is 00? Look up column A and find out which row corresponds to in hexadecimal 00. I think that doesn't take too long. Okay? No op, okay? Or nop, okay? So we know that the first location in RAM, which is location 0, has the content of 00. And according to the documentation, it does not do a single thing. Now, when I say it does not do a single thing, it's not exactly not really doing a single thing. There are side effects, okay? When I say it doesn't do a single thing, it means it does not update memory. It doesn't update or change any registers. It does not change the flag register. So it has no usable side effects, which is not the same thing as saying it does not have side effects. Is that okay? So we will be able to observe the side effects that are kind of like, well, but tech, that doesn't seem to do anything useful, okay? But it does have side effects. Are we good so far? Okay? All right. So now that we have disassembled 00 to be no op, we go back to the simulator and we go like, okay, so we are expecting none of the registers to be updated Now, when we say none of the registers, this time I have to be more specific because there are more registers than just the registers in the register bank. The register bank has registers A, B, C, D. Those are the software accessible registers. None of those should be updated, okay? But there are many other registers and they get updated, all the time, okay? So we'll see what other registers are going to be updated and how and why they got updated. The flags register should not be updated, okay? When I say the instruction doesn't do a single thing, the flag register, which is right here, should remain as is. And also at the same time, none of the RAM content over here should be updated either. Okay? But other than these few things, the rest of the processor actually will keep ticking and changing, and we'll be observing all kinds of changes as we execute the no op instruction. Are we good so far? Okay? All right. So where do we start? Okay? In other words, we look at this big picture here and go like, wow, that's a lot of stuff here, okay? So how do we figure out what the processor is going to do next, okay? The ROM is important, okay? But what we want to do is to find out what components are active at this point, okay? Now, you can look at ROM. So let's go to ROM first. So we go to the ROM, which is right here, okay? And you can see how the microcode pointer, which has 000 in it, okay? It is pointing to location 000 in ROM, which in return has hexadecimal 1080007 as its content. That content in ROM, now because the ROM is always enabled, so that means that content, whatever location is addressed, the content of that location is always output to the D port, okay? So if you say, okay, 1 is 0001, 0 is 0000, 8 is 1000, and so on, you will come to the same conclusion of what bits should be 1s and what bits should be 0 when we get to the splitters. Is that okay? So all of those things go to various places of the processor. And now we have to track down and say, okay, so what are we really telling the processor to do at this point? So the focus is to only on things that are enabled. Okay? If something is disabled, pay no attention to it. Okay? But if something is enabled, then you have to ask, how is it going to be updated? Are we good so far? Okay? Now the clock at this point is low. In other words, if I control T at this point, it's going to be a rising edge. All registers are sensitive to rising edge except for microcode pointer. This is the only register that is sensitive to falling edge. Okay? So this means, upon the next control T, which will cause a rising edge, whatever register that has enabled being 1 is going to be updated. So we want to pay attention to those. Okay? So now we look through the whole design. Okay? I understand it looks really busy, but once you know what to look for, it is not that difficult to read. Okay? We look at the register bank and we ask, is anything in the register bank going to update? Nothing, because the table of the entire register bank is a 0. So we know none of the 4 software accessible registers, A, B, C, or D, is going to be updated. Are we good so far? Okay. We look at the ALU. Okay. This is the ALU here. Its enable is also a 0. So we know nothing is going to be computed using the ALU because the ALU is off at this point. Okay. We look at some of the other registers. We look at the flags register. Its enable is also a 0. Nothing is going to update, okay? So we don't have to pay attention to the flags register. We look at the program counter over here, and it is also not enabled because PC enable is dark green. It's not going to be updated. So it doesn't look like we are going to do much, right? Then we start to notice that, hey, what about this instruction register here? It has got an enable of 1. So let me scroll down a little bit here so we can focus on that one. So you can see right here, the instruction register has an enable of 1. And because it is not the microcode pointer, which is the only one that is sensitive to falling edge, we know the instruction register is going to be updated. The question now is, how is it going to be updated? Okay, what is its new value? And how did it get that value? Is everybody kind of understanding the line of reasoning? If a register is not enabled, don't pay attention to it. Okay? On the other hand, if something is enabled, you need to track down things. So we know the instruction register is going to be updated. So now the question is, who is controlling the D port of the instruction register? Okay, we follow the wire, right? The nice thing about LogicSim is if you are in the poke mode, you can click on a wire and it will highlight the entire net. Okay, in other words, it will highlight what the D port of the instruction register connects to, and it will highlight all of that. That makes it easy to track down. Oh, okay, so we need to track down at least one of these things is going to specify how the instruction register is going to be updated. So what we do is we are just going to track it down, okay? So you might want to adopt a kind of specific way to track this down, okay? You can do clockwise, you can do some systematic way, top down or whatever. So I'm just going to look, over here and look at this one. This is coming out of a demultiplexer, but I don't have any concerns about this because the demultiplexer is off. You can see how the enable of the demultiplexer, register output 0EN, is off. Is that okay? So this is a dead end, okay? We need to look for something else. So the same wire also goes to the input of this multiplexer all the way to the left-hand side. I'm not concerned about that either. I'm looking for something that can output to this wire. This is an input into the multiplexer, so it is of no concern to me also. Is that okay? Does everybody understand that reasoning? I'm looking for someone who can specify content on this wire. The input of a multiplexer cannot do that. Are we okay? So we have two dead ends. This one is an output pin. An output pin cannot specify the content of a wire. It can only report back what is on the wire. So that is a dead end as well. So we have exhausted all the dead ends on this side of the picture. So our only option is now to look at the right-hand side. Okay? So we see that it is now connected to the data port of RAM. So now we have to ask, well, according to Sherlock Holmes, okay, once you have eliminated all the possibilities, whatever possibility is left, okay, no matter how unlikely, has got to be the only option, right? Not exact those words, but to the same effect, right? So now we say, what is RAM doing? Well, first of all, is RAM doing something? Is it being addressed? Is it enabled? Is it talking to us? The select port of RAM, which is SEL, is basically saying, is this component in use? Okay? It is an input pin. If SEL or select is a 0, that means RAM is not paying attention, not doing a single thing. But if it is selected, it's going to do something. Okay? The only question is, what is it going to do? The next line here, you see a little caret symbol. Can someone remember the context of this little caret symbol? What does it represent? Nope, it's not the reset. It is clock. So this is clock, which is not important in this particular operation, but we only have a clock whenever we have a component that has some operation that is edge sensitive. Okay? But it's not in this case. We look at the next wire or the next port. The next port says LD, which is load, LOAD, load. And whenever load is a 1, it specifies that we are reading from RAM. When load is a 0, it means we are writing to RAM. We are trying to update RAM. Okay? So in this case, are we reading from RAM or are we trying to update RAM? We are reading. okay? We're reading from RAM in this case. So wait, if we're reading from RAM, which location am I reading in this particular RAM component? Whose job do you think it is to specify the location that we are reading? The A port, which is the address port, okay? So the A port of RAM, just like the A port of ROM, specifies which location are we interested in, okay? All right, so we'll track that down, okay? So you can see how the questions are all leading to one another, because now that we know we are reading from RAM, the question is, which location am I reading, and who tells me to read that location? So those are the kind of consequences of asking these questions. So you're trying to figure out the operation of the processor through a series, or actually it's more like a tree of questions, okay? So now you have to track down this wire and go like, okay, who is specifying the location of RAM that I'm reading from? So we are not interested in the content of the location. I'm more interested in why are we reading that location, okay? So you can see how it is coming from a multiplexer, right? So if you see that the address port of RAM is connected to the output of this multiplexer, what is the next question you should be asking? What the input of the multiplexer is connected to, and what is the select bit of the multiplexer. Remember, a multiplexer is a switch. It has multiple inputs, one single output, and it is a switch to specify which one of the inputs connects to the output, right? So now our next question is to ask, which input are we connecting to the output? And the select is always the one under the gray dot of a multiplexer or demultiplexer. It is in light green. What does that mean? It's a 1. So we are selecting input 1 to connect to the output of this multiplexer. So we track down the bottom or the lower wire, which is this one here. Does it make sense? Yes. All right. So now we go, where does it connect to? These output pins are only here for debugging purposes, so they are not actually useful when it comes to, oh, maybe that is specifying the content of this wire. No, the output pins never specifies the content of a wire. They're only reporting what is the current content of the wire. So they're only good for probing, but not so much to determine the value. So we look at this wire. It connects to two places. It connects to the input of the adder. It also connects to the output of the program counter. So the program counter is telling us to read from location 0, 0, because the program counter as a register currently has 0, 0 as its own content. Are we doing okay so far? Okay. So anything that connects to the address port of RAM is basically serving as a counter, is serving as a pointer because it is telling us which location of RAM we should be reading. Is that okay? So now that we have answered the question, the program counter is telling us to read from location 0. So we look at location 0 because now we can say, what is the output of RAM in this case? Well, the output is the content at the addressed location, which is just 0, 0. You can click on a wire to see what is the content. And obviously, it is just 0, 0, not because the address port is 0, 0, but because location 0, 0 has the content of 0, 0. Is that okay? In other words, we just dereferenced location 0. And the value of dereference 0 is also 0 in this case. But that was a long answer to what question that we originally started with. Does anyone remember what was the original first question? Which register was enabled? The instruction register, right? So the instruction register is now going to be updated, but it is updated to the content of location 0, 0, which turns out to be also 0, 0. Is that okay? So when I do a control T, it is as if nothing happens, because we are updating instruction register, which currently has 00 in it, to 00. So we won't be able to see that particular side effect. Okay? But just for the experiment that we are doing today, I can go to the instruction register and just kind of force the content to 4E, just so that we can see when I control T, it gets updated to 00. It's just for that purpose. Are we good so far? Okay. Anything else? Okay, anything else that I missed? Well, this register is also enabled, but this one is sensitive to a falling edge, so we are not concerned about it with this control T. All right, so I think we are ready to type control T on the keyboard, or if you prefer, you can go to simulate and give it one single tick, okay, which is the same thing as typing control T as a keyboard shortcut. So there we go, control T, and you can see how the instruction register is now updated to 00 from 4E, because I just kind of forced the content of 4E into it initially. Are we good so far? Okay? So if you are taking notes, you might want to write down in your notes that we have just completed the fetching of an instruction, F-E-T-C-H-I-N-G. This is the fetch cycle of an instruction. The fetch cycle of an instruction is pretty easy. The processor is using the program counter to look up RAM to figure out, hey, what opcode am I supposed to execute next? That's the fetch cycle. Are we good so far? Are there any questions at this point?
So what it finds in the RAM, it sticks into the instruction register?
Yes. So it just read whatever it read from the location that is pointed to by the program counter,
Okay.
and that is now read into the instruction register.
Okay. And I guess that goes to the ROM?
Nope, not yet. Not yet. It will make itself to affect the ROM, but not right now.
Okay.
Okay? So if I were to take my own notes, okay, not that, but, okay, so I'm going to write my own notes here. The fetch cycle is doing this. It's doing the instruction register gets the dereferencing of the program counter. That's one way to look at it, because the program counter points to RAM, and we are using the program counter as if it is a pointer. Okay? Now, for those of you who refuse to see memory as memory, you can say the same thing like that. Okay? You can look at RAM as an array where the program counter is specifying the index into that array. So these two notations are somewhat interchangeable. I personally prefer the first one, using the dereference operator, because that really connects back to what dereference does in C++ and C. But if you prefer to look at RAM as an array and the program counter is specifying the index into that array, that kind of works out too. So this is up to you to decide which way you want to look at it. Are we good so far? This is a fetch cycle. Okay. So I'm going to switch back to LogicSim. So now what? Okay, we got a clock is high. So when the clock is high, most of the components are not going to do a single thing with the next transition, because most components are only sensitive to a rising edge. But there's only one thing that is sensitive to a falling edge, and that is the microcode pointer. Okay? So the microcode pointer, which is this guy over here, is sensitive to a falling edge, because that is how I set it up. The trigger of this particular register is sensitive to a falling edge. It updates on the falling edge. Are we good so far? Okay, so when I control T again, it's going to update. But I want to know how it is going to get updated. Okay, so same kind of reasoning, right? You look at a register that is about to be updated, you track down its D port and say, well, how is it going to be updated? Well, it's coming from the output of a multiplexer. So if something is coming from the output of a multiplexer, the next natural question to ask is, which input of the multiplexer, which means you have to look at the select input of the multiplexer, which is the one line that is under the gray dot. So the gray dot, or the line connects to the gray dot, is light green, which means it is one single bit, it is a 1. So that means we are connecting input 1 of the multiplexer to the output, right? So I don't really need to know what 0 goes to, I just need to know what input 1 is coming from, and that is coming from an adder, okay? This is an adder, okay? So adder has got two numbers to add. This is carry in, which is what we know as K0 in the discussion of carry look ahead. And this is the output. This is carry out, which is our K3 in the circuit that we built. But in this case, it's actually K8 because this is an 8-bit adder. No, actually, I take it back. This is a 12-bit adder. So this is actually K12. But we are not connecting the output to anything. We're only interested in the sum. So now we have to say, what is it adding then? Okay? Because now we have to look at the adding. So one input of the adder is connected to the output of the microcode pointer itself. The other one is connected to a constant of 0 with a K0 that is also fixed to be a 1. Okay?
Is that just
Yep, it's just doing an increment. But I want to make sure the whole class understands that is what's happening. Okay? Because it looks kind of mysterious, right? Because the microcode pointer has the Q port connected to the adder. The adder has the other input coming from the constant of 0. K0 itself is a 1, so eventually we're adding 1. Okay? The output of the adder is going to be whatever the microcode pointer has plus 1. Okay? That in return goes to the input 1, it goes to input 1 of the multiplexer, but because the select bit of the multiplexer is selecting input 1, so now the output of the multiplexer is outputting whatever the adder is outputting, which is 1 more than what the register has. Is that okay? Is that a problem? No, this is not a problem at all. So how come we don't have an infinite loop? How come we are not seeing the microcode pointer just continuously updating by itself like that? Because it's only sensitive to the edge. Okay. Now, is it a falling edge or is it a rising edge? That's kind of dependent on which register. But all registers only update on an edge. So right now, even though it's enabled, the edge is not happening, so it's not updating. Are we good so far? So when I control T again, okay, the microcode pointer is going to change from 0, 0, 0 to 0, 0, 1, okay? So, but because the microcode pointer Q port connects directly to the A port of ROM, what do you think you would observe in the ROM? Location 001 will be addressed. Are we good so far? So I'm trying to explain the mechanism, trying to predict what's going to happen next before we actually control T. All right? Yes. Okay. Any questions? Okay. So we do a control T, and sure enough, that's exactly what happened, right? But because you can see the content of location 001 is different from the content of location 000, so you can expect the rest of the processor to go through some different operations this time. Does that make sense? Okay. So now what do? We do the same thing that we did a while ago. Okay. We look at each major component, and then we figure out which one has enabled being a 1 that can potentially be updated, and then we start asking questions. Is that okay? All right. So we go through that exercise. Okay. So this time we are smart. We go to the RAM first because we used it last time, right? This time, RAM select is a 0. It's not selected. So the RAM component is inactive in this case. Okay, so that's kind of a dead end. All right, so what else should we look at? Oh, we can look at the ALU, not enabled. Okay. Registers, Nope, none of the registers, none of the software accessible registers are going to be updated because the register bank input select, input enable is a 0. Oh, darn it. Ooh, look like this one is enabled, right? The program counter is enabled. So the moment you find out that a register is enabled, and we are going to have an edge that will cause the update of the register, what question do you ask next? What connects to the data port? Very good. Okay, so now we have to track down what connects to the data port of this register that is going to be updated. Huh? Yep, exactly. So it connects to the output of a multiplexer, and the multiplexer has a funny name, for the select bit. It's called PC mux, okay? Which is the PC multiplexer, select bit. It's dark green, which means it's a 0. So this time we're connecting input 0 of this multiplexer to the D port of PC. So what do we do next? We track down input 0 of that multiplexer. There we go. We go like, hey, we have seen this before, deja vu, right? So this time we see that it's coming out of an adder, okay? The carry bit is a 1. Now, why is that a 1? It's not a constant this time, okay? It's because, it's an OR, PC inc or PC increment is a 1, address mux is also a 1, so it's going to be 1 or 1, which is a 1. But nonetheless, we are adding the program counter and 0 and 1 together. The output is then used to update the program counter itself. So that means the program counter is going to increment. Okay? Why do we want to increment the program counter? Because we just fetch that opcode. I don't need the program counter to keep pointing to the same location that I have already read. Is that okay? So this is an auto increment because that location is no longer of interest to me. I want the next location next time. So it's an auto increment so that we can get to the next opcode. Are we good so far? Okay. So we want to track down, do we update anything else? Okay, is there anything else that's going to be updated? Oh, the microcode pointer is enabled. Well, guess what? It's always enabled. Okay? But this one only updates on the falling edge, right? So we're not really exactly too concerned about it. Is that okay? So I can tell you none of the other registers are really enabled, so we're only incrementing the program counter at this point. Are we good? Okay, so we do a Control T, and this particular step has no specific name to it other than we're just incrementing the program counter so we can get to the next instruction, okay? So in the documentation of the fetch cycle, this is something that you can do, is to say this is a auto increment operation, or you can do the plus plus here, which is just a handy way of saying we're going to read whatever it points to right now, but at the same time or right after we read, we're going to increment it so we'll be ready to read the next location. So that's up to you. If you want to put PC after this assignment operation, that's fine too. Okay, they're equivalent in terms of what is actually happening. Okay. So now we're looking at a falling edge, right? So falling edges will only update the microcode pointer. So we know now we have to focus on the microcode pointer again, except that this time the multiplexer select is a dark green, which means we're reading from input 0. So we are not auto incrementing anymore, because we're reading from input 0, which comes from some really oddball thing, okay, that we call a splitter, except the splitter is merging in this case. But it has a very odd merge pattern, okay? Bit 0 to 3 is hooked up to just 0. So that means bit 0, bit 1, bit 2, and bit 3, they're all zeros. They're constant 0. Yep. Huh? Because this is 12-bit wide. the input, the ports are 12-bit wide with this multiplexer. Let me select it. Because the data bit is 12.
But if the microcode processor or the microcode pointer is only 3 bits, then how is inputting 12 bits not getting it?
It's 12-bit too.
What?
The microcode pointer is 12-bit wide.
Is it just only displaying 3?
It's displaying 3 hexadecimal digits. Because each hexadecimal digit is 4 binary digits, so we actually get 12 bits. I did not quite explain that part, and it's not visible because the number is too small to notice that. Yep. Okay. So now the question is, what about the other part? What about this part that says, okay, some of you cannot read it. It says bit 4 to 11 is coming from the tunnel that we call instruction, which is here. Okay. I could have just used a wire, but I just felt like using tunnels. Okay. So this is the Q port of instruction register, which is currently 0, 0, right? So that means we take bit 0 of the instruction register, and it becomes bit 4 of the microcode pointer. We take bit 1 of the instruction register, and it becomes bit, 5 of the microcode pointer. In other words, all this is doing is bit shifting by 4. It's left shifting the instruction register content by 4 bits to the left, and that becomes the content of the microcode pointer. Yes. So in your note here, okay, so don't copy it just yet, okay, because I'm going to do some additional stuff. So at this point, the microcode pointer is going to become the instruction register left shift by 4 bits. Okay? And this one has a name, okay? It's called a decode cycle of executing an instruction. Are we doing okay so far? So you might ask, why is it called decoding? Okay, it's not apparent with what we're doing right now, but with some additional examples, it'll be pretty apparent why it is called a decode cycle. Are we good so far? Okay. So we have fetch being the first one, decode being the next one. Okay. And if we go back to the to Logic Sim, so not quite excitingly, if I type Control T at this point, you would expect microcode pointer to be 0, 0, 0 again, right? So it's going to go back to location 0, 0, 0 in the ROM, which means we're going to fetch the next opcode. This is why opcode 0, 0 is known as no op, because it doesn't do a single thing. It just go like, do nothing, move on to the next instruction. Do nothing, move on to the next instruction, and so on. Are we doing okay so far? Okay. So are we ready to do a Control T just so that we can observe the microcode pointer is going to reset to 0? All right. So let's focus our attention over here and do a Control T. And not very excitingly, it is now back to location 0, 0, 0. But are we in exactly the same state as the beginning of this class? Exactly. The program counter is now 0, 1. So we are now ready to look at the content at location 0, 1 of RAM and execute it. What's going to happen?
Eventually we'll set the microcode pointer back to 0, 0, 1.
Yep.
And that will set the program counter to 0, 2. And it's just going to keep going back and forth and just
Yep.
flipping the microcode pointer back and forth between 0, 0, 1 and 0, 0, 0.
Yep.
While advancing the RAM and advancing program counter.
Yep. Exactly. So Control T, Control T. I keep Control T-ing here. And you can see it's really just executing every single location, and all of those are no ops, right? So it's just going to do this all the way until location FF in RAM, and then we'll add 1 to the program counter. Then you go like, aha, this time it's going to crash because you cannot add 1 to FF. Sure we can. It just rolls back to 0, 0. So this program is in super infinite loop, not because you specify an infinite loop, just because the address will roll back to location 0. You cannot really tell to stop other than stopping the auto tick. So if you want to observe visually what that looks like, I have to lower the tick frequency because otherwise it doesn't look interesting. So I have to lower it to something that we can perceive, using our eyes. 32 is probably doable. And then you can turn on the clicking. And you can see how it just goes on and on and on. Okay, we'll wait a little bit here. We got some time to burn. Yep, just keeps going. Because RAM is all 0. RAM has 256 locations of zeros. Okay, we're getting there. Okay. And then it goes back to location 0. Yeah. If you just missed what happened, it's okay because it's all recorded. You can slow-mo it. Yep, exactly. You can slow-mo the whole thing. Okay, so not very interesting, is it? Okay, but it demonstrates the two important cycles in instruction execution: fetch, decode, fetch, decode, fetch, decode. Yep.
And if you would set any of the locations in RAM to 0, 1, it would just stop there, right?
Right. Exactly. Okay. So not so interesting. So let's do something that's more interesting. So let me look at the time. 6:31. Yeah, we can do this. All right. So we're going to look up the opcodes table, and let's do something that is slightly more interesting. So let's do the LDI instruction, this one here. Okay. So the LDI instruction is load immediate. Okay. So you can see the instructions that ends with an I, when the mnemonic ends with an I, those are the only instructions that has an I instead of a Y when you specify what it can do or what the parameters are. An immediate is basically just another word of a constant. Okay, so whenever you see I or immediate, you basically just say, oh, it's a constant. So this is one way, and the only way you can put a known constant into a register, a software accessible register, meaning register A to D. Okay? So pick one of the 4 registers and pick the constant that you want to initialize the register to. That's what this instruction does. Is that okay? All right. So we're going to hand assemble this particular instruction. So we'll go ahead and use Notepad over here. So for the time being, we're going to move on to talk about the assembling of LDI. Let's say I want register C to now have the value of 79 in decimal. Okay? But I want to do it by hand. Okay? The assembler can totally do this, but I don't want the assembler to do it. I want to do it by hand. So now what do? Well, we look at the bit pattern. We look at column A. Column A says whatever register X is, it's going to change the bit pattern XX. If X is A, XX is going to be 0, 0. If X is B, then XX is going to be 0, 1, and so on, right? So in this case, register X is C, so that means XX is going to be 1, 0. Very good. So the opcode is 0, 1, 1, 0, 1, 1, 0, 1, 0. Okay? These 2 bits are corresponding to XX, which specifies, I actually got it. This is what I call debugging. Yeah. That's the myth. I'm not really sure whether that was the case or not. But considering computers back in those days, the way you specify the behavior of a program is by wiring, I can kind of see that happening. Possibly. Okay. So we got this opcode here. But when you look at column C, it's really kind of awkward. Okay. It doesn't just say that X is PC, X is I. It's not X equals I. Instead, it says x equals PC plus plus and then dereference. It's like, what the heck? All it's saying is the next location following the opcode is where the constant goes. Okay? That's what it's saying. The program counter, because of the auto increment after the fetch, is already now pointing to the next location. That location is containing the constant that we want to put into the register. Then how come we don't just say, star PC? How come it's star PC plus plus? Because if we do not do a plus plus, then in the next fetch cycle, we'll be looking at the constant as if it is an opcode and try to execute it. That would not be the right thing to do. So that's why we have to auto increment PC again so that we do not look at the constant as if it is an opcode in the next fetch cycle. We good? Okay. So that means 79, this is 1 byte. So the next byte is going to be 79 as a byte. So 79 as a byte has no 128, has 164. Then we have, 15 left? Oh, 15 is easy. Okay? Because 15 is 1111 in binary. And then the 0, 1, this is 128, this one is 64. 64 plus 15 is 79. Okay? All right, so that means in hexadecimal, we have a 6E and then a 4F over here. Okay? I'm pretty sure I talked about the lookup table already. So if you have a lookup table, it's just looking up the bit pattern and find the hexadecimal digit. If you do not know what lookup table I'm talking about, you kind of have to re-watch the videos. Okay? So 6E4F is what we want. Okay, so we can now go back to the logic sim. Okay, we do a Control R first. Okay, reset the entire thing. And then we go to edit content. And then we specify the 4, 6E4F. Thank you. 6E4F. Okay. Well, since I told you guys not to trust me, what do you think my answer is to that question? We don't need that. Okay. Yeah, we want to execute this really slowly, so it's not like I'm going to turn on the clock and let it auto clock, okay? All right. So what about this time? What is going to be happening? Same thing, okay? RAM is selected. We are going to read whatever the program counter is pointing to, which is location 00. The content is 6E. We'll put it into the instruction register. So I'm just fast tracking that portion because I explained it in details last time. So I'm not going to go through the detailed explanation this time. So Control T, okay, which means the instruction register should now be, not yet. Did I Control T? Nope. I did not Control T because the clock is still low. So Control T, there we go. So rising edge, the instruction register is updated to the content of the location that the program counter is pointing to. Okay, that's all good. And then Control T again, the microcode pointer should just increment to the next location. So Control T, sure enough. And now we are decoding it. Okay, this is when things gets a little bit interesting. Okay, so on the next rising edge, okay, the program counter is going to increment because that's the auto increment, right? So Control T, and you can see how the program counter is now pointing to location 01, which is where the 79 is stored. So the program counter is currently pointing to the correct location of RAM that has the content or the constant that I want to put into register C. Okay? But the more interesting question is, what about the falling edge? Okay, because we know the microcode pointer is updated on the falling edge. So this time it's going to update to, guess what? 6E0. 6E0. Because the 0 is the least significant 4 bits. 6E are the more significant part of the 12 bits, and then the 0 is the least significant because it is bit 0 to bit 3. Okay? Does everybody get that part? Why the microcode pointer should now be updated to 6E0. The 6E, which is from bit 4 to bit 11, is coming from the instruction register itself. The 0 is coming from the constant 0, which is going to bit 0 to bit 3 of the splitter. Are we good? Okay? So you go like, okay, big deal. The microcode pointer is now 6E0. But that means over here in the ROM component, we'll also be looking at 6E0. This is decode, okay? But this time it is kind of more obvious what decode is really doing, because it is basically going to the location where I have a bit pattern that specifically says, put whatever the program counter is pointing to into register C, and then auto-increment the program counter. That's what this gibberish is saying, okay? 1D80056 is telling the processor to do just that, okay? Go to whatever location in RAM that the program counter is currently pointing to, get that content, put it into register C, and then auto-increment the program counter. How does it get it done, right? So we track down whatever thing is active, okay? This time we can see that, hey, the register bank is active. We are updating something in the register bank because input enable is a 1, okay? So what question do we ask automatically now that we know a register of the register bank is getting updated? What should we ask next? Sorry? We ask 2 questions, right? Which register of the register bank is getting updated? And 2, who is supplying the value to update that particular register? Okay? So you can write it down on a piece of Post-it if you're trying to reason out these things. You can just write down all the questions, track down each and every single one, and answer those questions. Is that okay? So we'll answer the quick question first, okay? Which register is getting updated? That is the job of RISEL. And I cannot see this one, but I can see this one over here. So when I use the poke tool, it says register C, because 10 is corresponding to register C. So we know register C is the one that will be updated on the next rising edge. Okay, first question answered, cool. Second question, who is specifying the content to update this particular register? So now we have to track down this wire over here. It comes from a multiplexer, okay? So now the next question is to ask is, what is the selection of this multiplexer? RIMUX is a 0, so which means that means we have to track down input 0 of this multiplexer. Now, if you are thinking, but Tech, it looks like you're using the same reasoning over and over and over again, I'm bored, then my comment is to say, that's good. That's what I'm expecting, okay? Because if you think that this is the same reasoning that we have gone through, I know this already, that's actually a good thing, okay? Because we did go through the same kind of reasoning, not applied to the same component, but the same reasoning technique nonetheless, okay? So we track down these wires, okay, and we look for one thing that can drive, one thing that can specify content onto the wire that is currently highlighted, okay? So once again, we do it kind of systematically. We look at this one and go like, no, that's not going to do the job. because we are trying to look at something that is an output, okay? This is an input into a multiplexer. That's not our answer. That's a dead end. We look at this one over here, same thing. In fact, that's where we came from, okay? So it's not going to answer the question. We look at this one over here and go like, well, maybe, but no, because this particular demultiplexer is turned off. RO0EN is off. That multiplexer is just going like, I'm not going to do a single thing. Okay? None of its output is actively trying to specify a content. So once again, another dead end. We scroll to the right-hand side. Okay? We go like, okay, you're the last one, RAM. Are you outputting something? So now we have to say, well, is RAM even awake? Yes. RAM select is a 1. What are we asking RAM to do? That's the job of load. Load is 1, which means we're reading from RAM. If you're reading from RAM, the content of the location that is addressed is going to be presented to the output. So now we know D, the D port of RAM, is the content of the location that is addressed. Yep. But wait. We are not done answering all the questions. Because the next question now is, wait, we are reading from RAM. We know RAM output, the D port of RAM, is used eventually to update register C in the register bank. That's all cool. But who is controlling the location from which we are reading in RAM? That's the address port, okay? So now we have to track down who is driving or specifying the address port. And if you say, Tech, but you have gone through this already, good news. That's good, okay? So we look through this. We go like, oh, okay, it's coming from the output of a multiplexer. So we look at the multiplexer select bit, which is 1. So now we track down input 1 of the multiplexer. It goes back to the program counter. Cool. So we now explain why we are reading from the location that the program counter is pointing to in order to update register C, okay? But you look at the program counter and go like, but the program counter itself is getting updated too. See the PCEN here? That's a light green. It is also being updated in the next rising edge clock. So what is happening here? So now we have to track this down. Okay, we track down, okay, how are we updating the program counter? Yep. It's getting the input 0 of the multiplexer, which is coming from the adder, and the carry in is a 1, so that means the program counter is auto-incrementing. You go like, but Tech, you mentioned that whole line of reasoning about 10 minutes ago? Yes, I did. Okay, so the program counter is going to be, wait, but don't we have a problem here? Because are we really sure that the program counter incrementing is not going to affect the updating of the register over here? Well, the answer is no, okay? The answer is no because they're both ready to go, okay? In other words, the data to update register C is already presented to the input of register C. The data that is about to update register program counter is already presented to the input of the program counter. Okay? They both have a propagational delay. So yes, the program counter will increment from 0, 1 to 0, 2, but not in time to affect how we update register C in the register bank. Is that okay? All right? Because this is kind of the mysterious part. It's like we are changing one thing that is controlling how we change the other thing. So which one goes first? Well, they're all happening at the same time. Okay? So when we do a control T at this point, this is called execute. Okay? So we go back to the notepad here, and then we now have an execute cycle. Now, the execute cycle is hard to describe. It's hard to describe it in general because it depends on what opcode you're executing. Okay? The opcode that we are executing right now, this is how we can describe it. Register C is getting whatever the program counter has, but the program counter itself also gets auto-incremented after the operation. Okay? But that's not the same with the other opcodes. Okay? With every single opcode, they fetch the same way, they decode the same way, but execute is specific to each opcode. So I'm only describing the execute cycle for this particular opcode the way it is. All right. And it's OK. We still got a minute or so, and I know you don't have another class after this. Don't ask me why, but I do. OK. So Control T, OK? So this is another Control T, OK? Now we get to observe the actual result of executing this instruction. Program counter is now a 0, 2 because it auto-incremented. And then we go into the register bank, and we can now observe that register C is now 4F. In fact, we have just read the content at the location into that register. So is that OK? Yeah. All right. OK, just one more thing. Yep, go ahead.
Is the property the delay caused by the adder then? Like we see the delay for the whole thing to happen. Is that because we're using an adder to implement?
I don't think so. But there's one more thing that is really crucial is what happens now? I mean, we are done with executing the LDI instruction. So what's going to happen next? So once again, the falling edge only affects the microcode pointer. It is looking at the input one, which is just auto-incrementing. So you would expect the microcode pointer to increment to location 6E1, right? And then whatever is right at location 6E1 will be selected. Okay? So Control T, ding. It's like, what just happened? Because at 6E1, okay, the location at 6E1 is 2 followed by all zeros. Okay, 2 followed by all zeros is which bit? Which bit is on? We know one and only one bit is on in this case. We got 1, 2, 3, 4, 5, 6. We got 6 hexadecimal digits. So 6 times 4 is 24, right? And then if it's a 1 over here, it's bit 24. If it's a 2 here, it is bit 25. So bit 25 was a 1 when the microcode pointer is 6E1. What does that mean? OK, well, let's look at the splitter here. This is bit 25. Bit 25 was a 1. It goes into an OR gate, which means the output of this OR is going to be a 1. That 1 goes into, what is this thing here? It has a label of 0. What does it do? It's the reset. OK, it's the reset of the microcode pointer. It always resets to 0. And that's why it actually happened, but it was so fast that we could not see it. Is that OK? So now, where are we now? We're back to the fetch cycle. We're now ready to fetch the opcode at location 002 in RAM, and then just do the whole thing again. Are we good so far? So your lab tonight, OK? There's a new lab for tonight. It is going to open when I get to the lab. This one is about tracking the execution of a few instructions, and LDI is one of those. So that's good. I just did the whole thing in class. The other instruction, I think one is LD and one is ST. So the way you can try to understand those instructions is to do the same thing that I did, clock by clock, look at the enable, track down the wires, and go through the whole thing. That is how you study from here on. Okay? It's not reading something. It's not trying to memorize something. It is to reason out, to figure out how the processor works. Okay? So I will go to the lab as soon as I shut down here.